The inverse image is always left adjoint to the push forward, but sometimes it is also a right adjoint to some functor, and this functor is called the extension by zero. When I is an inclusion open subset to Y, let's define the extension of I by zero, noted I shrink, in 2 steps. Let F be an OU module. For open subsets W in Y, we first define a I shrink pre of F by setting sections on W to be F of W if W is contained in U and 0 otherwise. The restriction maps will be either the restriction maps of F or trivial restriction maps if there are zeros involved. This I shrink pre is not necessarily a sheaf. It is a pre-sheaf, and the counterexample will be given by the continuous functions on R. We let topological space Y to be the real line, and this open subset U be the positive real line. And we let the sheaf F be the sheaf of continuous function on the positive real line. So that I will be the inclusion of U to Y. By our definition, shrink pre F of W will be either the continuous function on W if W is contained in the positive real line, or 0 otherwise. Now let's show this is not a sheaf. We decompose R into 2 open subsets, one from negative infinity to 1, and second from 0 to positive infinity. And we consider 2 functions. The function f1 is a 0 function taken from the sections over the interval from negative infinity to 1. By definition, this is 0 because this interval is not contained in the positive real line. We take f2 to be a piecewise function. This is a continuous function. So f2 is indeed in here. Note that 1 and f2 agree on the overlap of their domain, which is the interval from 0 to 1. However, f1 and f2 cannot be glued together to give a function f in here, because this guy is 0 by our definition. This f has only one choice, the 0 function, but the restriction of 0 function to here is not f2. So the gluability, this example fails. So On this I' pre of f, we will apply the sheafification to make it a sheaf. We define I' of f to be the sheafification of I' pre of f. This can also be written as sheafification composed with I' pre applying to f. Here's an issue. We start with f as a OU module, and I' pre-f is a pre-sheaf OY module, which can be clearly seen from the definition in here. The scalar multiplication for this will be either the original scalar multiplication or the trivial scalar multiplication. A scalar multiplied by 0 will be defined to be 0. Now here's a question. Can we prove I' we have just defined to be a OY module? The answer is yes. Actually, we can show that the sheafification of a pre-sheaf module will be a sheaf module. Let me write this as a lemma. Let X be a topological space, and OX be a pre-sheaf of rings on X. Let F be a pre-sheaf OX module. Then the sheafification of F is a sheafification of OX module. The proof of this is not hard. We will use the compatible germs. The sheafification, by definition, is the compatible germs in the product of stocks. Since the compatibility of germs are preserved by addition and multiplication, so this is still a ring, and this still has a abelian group structure. The scalar multiplication of elements in this scalar ring and the elements in this abelian group is defined in the following obvious way. If those germs are compatible, then it's easy to see those germs are also compatible. Meanwhile, there's a commutative diagram we need to check. But the commutativity of this diagram should be obvious, and we skip the verification. Therefore, the sheafification of F is really an OX sheafification module. So this I'(f) is an OY module. Here, OY is already a sheaf of rings. Now let's compute the stock of I'(f). The stock of I'(f) at Q is equal to the stock of the sheafification of I'(pre) F at Q. But we know the sheafification preserves the stocks, so this is naturally isomorphic to I'(pre) F sub Q, the stock at Q. But this, if we go back to look at the definition, is equal to the stock of F at Q if Q is in the open set U. Otherwise, it will be 0. Because if Q is not in U, then any open subset containing Q will not be contained in U, and therefore I shrink pre f of W is always 0, and if you take the colimit, it will still be 0. So it is 0 if Q is not in U. It follows from part B that I shrink is an exact functor. This is because the exactness always be checked at the level of stocks. Suppose we have a short exact sequence of OU modules. Apply I shrink to this sequence. We want to prove this is also a short exact sequence. To this end, we take the stocks. It is always an exact sequence because there are only two possibilities. Either they are equal to the stock of those guys, just form an exact sequence because the original sequence is exact, or all of them are 0, and from which we get a trivial exact sequence. Since exactness can be checked at the level of stocks, we get this sequence exact. By the exercise 2.6.d, we know if I is the inclusion of an open subset to a topological space, then the inverse image of a sheaf on Y is a restriction of this sheaf to this open set. And now we want to extend this by 0. We expect that this guy will be somehow related to G. And it turns out that there's an inclusion of this extension of restriction into G. And now let's prove this. As before, we will use the compatible germ language to describe it. For any open subset W, G of W is isomorphic to the compatible germs in the product of stocks. And how about this guy? The section of this guy over U is the extension of the restriction of G of U, which is isomorphic to the compatible germs in the product of the stocks of I shrink pre of G restriction of G to U. This is actually the definition for the sheafification. Now, what is the stock of the I shrink pre G restricted to U? By part B, we know it is equal to the stock of this sheaf if Q is in U and 0 otherwise, where U is the domain of this F, is the domain of this sheaf F. Therefore, this guy is equal to the stock of G at P if P is in U and 0 otherwise. So now we can define an inclusion from this to this. The inclusion is defined by sending the product of compatible germs in here to the corresponding product of compatible germs in here through this identification. Note that S sub P is 0 if P is not in W intersection U. Now let's prove this is a short exact sequence. Again, we will verify the exactness at the level of stalks. Let's first look at the stalk of this guy as a point Q. Notice that J inverse of G is a sheaf over Z. We consider this as a whole, a sheaf over Z. By definition, the stalk at Q is a colimit of this guy, where V ranges over all open neighborhoods of Q. And now by the definition of the push forward, we get the colimit of J inverse G of J inverse of V. But J is an embedding from the complement of U to Y. So this guy is really equal to the intersection V. We have already seen how to deal with this guy before. It will be equal to the one-point set if Q is not in Z, and the stalk of J inverse G at Q if Q is in Z. Here we use the fact that Z is a closed set. By the exercise 2.6.c, we know that the stalks of the inverse image sheaf are the same as stalks of this sheaf. And in our case, this pi is an inclusion map. So we get, if Q is in Z, then G sub Q is same as J inverse G sub Q. Now, we can replace the Z here by U complement. So the stalk of this guy at Q will be trivial if Q is in U, and the stalk of G at Q if Q is not in U. Okay, now let's compute the stalk of this guy. By one of the previous exercise, I inverse G, I is an inclusion from the open subset U to Y is equal to the restriction of G to the open subset U. And by the part B of this exercise, the stalk of this guy at point Q will be equal to the stalk of this guy at Q if Q is in U. But the stalk of this guy will be precisely G sub Q when Q is in U. And it is 0 when Q is not in U. If Q is in U, then we get the sequence 0, G sub Q, 0, and 0, which follows from here. This guy will become G sub Q. And this guy, the stalk of this guy, will become trivial. This arrow is an isomorphism because of the proof of the first part of this part D. So when P is in U, then there's isomorphism between the stalk of this guy at that point and the stalk of this guy. So this is an isomorphism. So this is an exact sequence. If Q is not in U, we will get the sequence 0, 0, G sub Q, 0. Because when Q is not in U, the stalk of this guy at Q will be 0. And the stalk of this guy will become G sub Q. This arrow is an isomorphism because of the proof of the part B of the exercise 2.6.f. In the proof, we see there's an isomorphism at the level of stock when Q is in Z, i.e. Q is not in U, because U is a complement of Z. And for the same reason, this arrow is an isomorphism. So this sequence is also exact. We have proved for every Q, the sequence at the level of stock at Q is exact. So this sequence is exact. And we are done.